Alright, hi everyone. So welcome to the second lesson for topic 2 kinematics of motions in straight line. Alright, so as usual, let's try to look at the learning outcome of the lesson. So in this lesson, we are going to learn how to sketch and how to interpret a displacement time graph. Okay, so in short form, sometimes we will just call it as DT graph. So the other one is velocity time graph, which is the VT graph. Okay, so we are going to learn how to interpret and then to understand these three important key points here, which that how to find the displacement from a velocity time graph, how to find the velocity and acceleration from a dt graph and vt graph respectively. Okay, so we are going to look at it one by one. All right, so let's start with the introduction. All right, let's try to look at the first type of the graph. So the first one is displacement time graph. So this kind of graph is used to show the position of a particle in one dimension along the straight line. Okay, so I hope that you still remember what is that meant by one dimension. So meaning it's either going to right hand side as positive, then left hand side will be negative, or up is positive, then down will be negative. Okay, so we are not looking at any 2D or 3D spaces. Okay, so in a displacement time graph, so as shown here, the horizontal axis shows the time. All right, so the short form will be a t. Okay, then the vertical axis will show the displacement. Okay, and the displacement will be represented by s. Okay, so these are some special situation where you will see the graph. Okay, so when the graph is horizontal, so it means that if let's say you have this ST graph, right? So which look like this, so it's a horizontal graph. So it actually indicates that the displacement is unchanged, right? Because if let's say this is from the time from 0 to 5, so it remains at the position of 10 meter. So you can see that the displacement is unchanged. So if let's say the displacement of the particle is unchanged, so meaning that the particle is actually at rest. Okay, so at rest meaning it is not moving to anywhere. All right. Okay, so if the graph is not horizontal, it indicates that the position of the particle is changing. All right, so no matter we are talking about any type of linear graph, so things like this, or even things like this, or even like graph that looks like a half quadratic. Okay, so as long as the line is not horizontal, it indicates that the position of the particle is actually changing. So the steepness, meaning the gradient of the line, indicates how quickly the position change. So you can imagine, right, if let's say this is all from 0 to 5, this is 0 to 5 as well, and this is 0 to 5. So you can see that perhaps here it reaches 5 and here it may reaches like 8. Okay, then this is another one. So you can see that this particle used 5 seconds to reach 5 meter. So this particle used 5 seconds to reach 8 meter and so on. So the steeper the gradient or the steeper the line, it means that the position of the particle is changing faster and faster. Okay, so that's why you can see that if let's say this steepness indicates how quickly the position is changing, what is actually the concept that tell us how quickly a particle move? It's actually velocity, right? Velocity tell us that how fast an object move. So in the previous lesson, we know that velocity tells us the rate of change of the displacement over time, right? So by using the same idea, if let's say I have this particle move 5 meter in 5 seconds, which it also tells us that the velocity is actually 5 meter divided by 5 seconds, right? So that's why velocity is actually the gradient of the displacement time graph. Okay, I guess it's quite easy. Yeah, so the horizontal axis meant for the time, the vertical axis meant for the displacement, and the gradient because you are using the displacement to divide the time. So that's why you are getting the gradient. But of course, we are talking about a constant velocity. So which means that if let's say you have different number of velocity that involved, then we might need to use the idea for average velocity already. Okay, All right, so a straight line on a displacement time graph indicate a fixed gradient, right? So no matter how is your graph, so no matter it's either like a horizontal one or it's like this one or it's like the other way around. So since they are all straight lines, so which means no matter where you are trying to measure it, right, they will still give you the same gradient. So that's why if let's say they give you the fixed gradient, which means that they give you a constant velocity. Okay, so which means the velocity doesn't change according to the time. So if let's say you have a curved line, so for example, if let's say your graph looks like this, okay, so obviously you can see that the gradient changes, right? So for example, from here and when you compare to here, so obviously the gradient change. So the curved line indicates if let's say the gradient change, meaning that the velocity is changing. Okay, but in this, I mean, in our M1 syllabus, our ST graph and DT graph, will be sorry, our ST graph and also VT graph will mainly focus in the constant one. So which means that we are going to look at a straight line rather than a curved line. So for a curved one, it's going to be a variable for the acceleration or velocity already. So for that part, we'll try to discuss it in the last lesson for this chapter. And for that part, we will mostly use differentiation and integration to help us rather than drawing a graph. Okay? Alright, so that's the part. So now we'll be looking at a simple example where we try to read or we try to interpret a displacement time graph. Alright, so let's try to look at some important information that we can extract from this graph. Alright, so we can see that this is a displacement time graph. Okay, so there are few information that we are going to look at later. So we have pathway diagram, then how to find the total distance, the total displacement, the velocity, and also the average speed and average velocity. Okay, so let's start with the first one, the pathway diagram. So this is basically a diagram that shows us what is the change, how is the change of position of the particle based on this graph. Okay, all right, so let us try to draw a straight line first. So this is our pathway. Okay, so we need to have the origin, right, as usual. So this is the part for origin. So some of the important information that we can get is the maximum displacement is 5. Then you see on the other side, on the opposite direction, the maximum is -2. So we need to have some important key point here, which is -2 and also 5. Okay, so now let's look at the time. Then after that, we try to indicate the position for every second. Okay, so let's start with the first one. So when t equals to 0, where is our particle? It's actually at the displacement of 0. So that's why when t equals to 0, the particle is at the origin. Okay, then after that, what happened? After that, when t equals to 1, the displacement of the particle become 5, right? So that's why the particle eventually move to the right hand side as positive. Then after that, it comes to this place, and this is t equals to 1. Okay, so it reaches the displacement of 5. Then after that, what happened during this place? So you can see this is a horizontal line. So which means from t equals to 1 until t equals to 3, there's no change in the displacement of the particle. So that's why the particle just stay here until another t equals to 3 as well. And after that, what happened? You can see that the gradient is the other side, right? So which means they will have a negative velocity. So now the displacement also move from 5 goes back to 0. So you can imagine that there's like a U-turn for this object going back to the origin. Okay, is that all right? So going back to the origin. So now this particle going back to the origin when t equals to 5. Okay, and after that, the particle also continue to move to the negative direction until the displacement of -2. So it continue to move until here. So which is when t equals to 6, the displacement of the particle is -2. So the particle now is here. After that, it continued to move. It didn't stop, right? So it continued to move, but this is a positive velocity, and you can see that the displacement changed from -2 to 0. So you can see that the object change direction again and comes back to the origin and reaches the origin when t equals to 7. Okay, so I think this should be quite easy. So now let's try to look at the second one, which is the total distance traveled. Okay, so for total distance traveled, right, it is very helpful for us to check for the turning point for the graph. So for example, from this graph, right, the turning points happen here, 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 and also here. So which means we can try to see for the constant part. So for example, from here to here, obviously you can see that from t equals to 0 to t equals to 1, the particle actually travel 5 meter. Then after that, it at rest, right? So meaning that our first distance will be 5. Okay, from t equals to 0 to t equals to 1. Then after that, it rests for 1 to 3. So that's why the distance is 0. Then after that, let's try to look at the second part. The third turning point is actually from here to here. So you can see that from t equals to 3 until t equals to 5, how far did the particle actually travel? Is from 5 until 0, right? And you must remember, for distance, we talk about the magnitude only, so we do not need to indicate negative here. So it's another 5 meter. So it also aligned to what we draw here, right? From 0 to 5, then from 5 to 0. So it's 5 plus 5. Then after that, let's try to check on the other turning point from here to here. So from 0 to negative 2, it moves another 2. So the same thing, from negative 2 back to 0, it moves another 2. Okay, so you can get the answer of 14 for the total distance. So you can try to check over here as well. So 5 plus 5 plus 2 and then plus 2. So this is how you get 14. Okay, so now let's try to look at the displacement. So you must remember the total displacement we are referring to what how much is the displacement if we compare to the original position of this particle. So you can see, right, this particle actually starts here and it ends at here. So is there any changes for the particle? Sorry, is there any changes regarding to the position of the particle? Yeah, so you can imagine that there's nothing changed. So same like what we have drawn here. So the initial position is here and the final position is also here. So that's why the total displacement is actually 0. Okay, so I hope that you can roughly get the idea here. So the difference between distance and displacement when you try to read it from the displacement time graph. Okay, so now let's try to look at velocity. So for velocity part, we are referring to the constant velocity. So which means we are not looking at, we will be only looking at average velocity in the last part. Okay, so for velocity, you can see that all the timing that I write here is regarding to a stage where they have a constant velocity only. So for example, from t equals to 0 to t equals to 1. So which means from here to here. So you can see this is only one straight line. So which means for us to find the velocity, we need to get the gradient. Okay, so for this gradient, I think it's pretty straightforward. So which means that it's going to be 5 minus 0. And after that, 1 minus 0. Then this is how you get 5 meter per second. Okay, so you can always check it with your graph again. So this should be a positive graph. So that's why your answer is correct. So the second one is from t equals to 1 to t equals to 3. So you can see from here to here. Okay, so this is a horizontal line. So obviously in terms of mathematics, you already know that a horizontal line will have a gradient of 0. So if let's say you're not sure in your exam, then you just calculate the gradient. So which means there's no change in the y coordinate, right? So from 5 to 5. Okay, and the time, the x coordinate will be from 3 to 1. So you can get 0 over 2 that eventually give you 0 ms per second. Sorry, 0 meter per second. Okay, so that's correct as well because the particle doesn't move, right? So if the particle doesn't move, which means the velocity will be 0. Okay, so now the last part, let's try to look at t equals to 3 to t equals to 5. Okay, so it's regarding to here. Okay, so obviously for this line, you know that you will have a negative gradient. So the x coordinate here is 3 and then 5 for y coordinate, and here is 5 and 0. So the same thing, let's try to calculate the gradient. So it's going to be 0 minus 5. Okay, and after that 5 minus 3. So you will be able to get a negative number. So over 2. So that's why you will get negative 2.5 meter per second. Okay, so that's the idea for velocity. So for velocity, you need to talk about the positive and negative as well. So you see for this part, right, I didn't ask questions like, oh, how about from t equals to 3 to t equals to 7? Because you can see that the velocity keep on changing here. From this one means one velocity. This one is another velocity because the steepness change. And here obviously is another velocity. So that's why for this case it's going to be the variable the velocity is not a constant anymore. So that's why we cannot straight away get the velocity. We only can calculate the average velocity, which we are going to look at it now. Okay, so how about for average speed and average velocity? So let's try to look at the average speed first. So average speed, we are talking about the distance divide the time, right? Velocity is displacement divide the time. So for the first one, from 0 to t equals to 7, so which means from here up to here, so which is the total distance, which we already got it here. Okay, so we can straight away use the answer. So the total distance from t equals to 0 to t equals to 7 is 14, and then the total time here is 7 seconds. So that's why I can get the average speed as 2 meter per second. Okay, then after that same thing, we move on to the next one. So if let's say is t equals to 3 to t equals to 6, then what happened? Okay, so you can see t equals to 3 is here. So yeah, I'm just trying to plot the turning point here, and t equals to 7 is here. Okay, sorry, is t equals to 6, so that's why it's here. So what is the total distance travel? So you can see that the position is at 5, then after that went to -2. So the total distance, it will be 7. Okay, or you can just use 5 and then minus -2, then you will be able to get the answer as well. Okay, so what is the total time? So it's 6 minus 3, right? Then it will be equal to 7 over 3. Okay, so I'm not going to change it. If let's say you want to change it, then it will be 2 and then 1 over 3, so 2.33 meter per second. Okay, so that's the average speed. Because you see, referring to the graph, you will have two different velocity that involve here. Here, the gradient here and the gradient here is actually different. Okay, so now let's try to look at the last one, t equals to 3 to t equals to 7. So which means it's here up to here. Okay, so you can see that from 5 to -3 is going to be 7, and 7, then -2 going to back to 0, right? So it's going to be another 2, so in total it will be 9. Okay, so 9 over, then the total time involved is 7 minus 3. So this is how we can get 9 over 4. Okay, so this will give you 2.25 meter per second. Okay, so now is the last part regarding to the average velocity. So average velocity, we need to talk about the net change of the displacement divided by the total time. So what is there any changes for the displacement from t equals to 0 to t equals to 7? So we can try to see t equals to 7 is, t equals to 0 is here, and t equals to 7 is here. So there's no net change happen, right? Because the initial is 0 and the final is 0. So that's why the displacement involved is going to be 0. So divide by the total times 7, so we are going to get 0. Okay, so the average velocity is 0. Then after that, the next one is t equals to 3 to t equals to 6. Okay, this is the special one. So let's try to look at this. So you must remember we are comparing to the initial for the time. So meaning that we are now looking at t equals to 3 and t equals to 6, right? So we cannot look at t equals to 6 and we say that the total displacement is -2, because the initial that we are comparing to is no longer t equals to 3, it's no longer t equals to 0, it's going to be t equals to 3. So that's why it's 5. Then after that, now it become -3. Is there any changes of velocity? Is there any changes of displacement occurs here? Yes, there is, and it's from +5 to -2. So what is the net change of the displacement here? It's going to be -7. Okay, so I hope that you can see the difference between the average velocity and the average speed here. So for this one, we talk about the difference as well, but we don't care about the direction. But for this one, we talk about the difference and we talk about the direction. Okay, so now and okay, I need to show you that you can see this one, you should always change it to negative, right? But it doesn't apply for everything because this is eventually because of the change of position is just from positive to negative. But for the last one, it's going to be different. Why is it so? Because when t equals to 3 is here, and t equals to 7 is here back to 0. So how much is the change of displacement involved? From 5 to 0, correct? So that's why when you try to calculate it, the final is at 0, then the initial is at 5. So that's why then divide by 7 over 3. 7 minus 3. So you can get negative 5 over 4. Okay, so this is how you can see the answer is totally different. So you must make sure that you understand what is that meant by the distance and what is that meant by the displacement and how is that different. So negative 1.25 meter per second. Okay, sorry, please check this out. I think I left out the negative here. Okay, negative 7 over 3, so negative 2.33. Alright, so that's the part for displacement time graph, and now we will be looking at velocity time graph. Okay, so this is a second type of graph, which is velocity time graph. So displacement time graph shows the position and velocity time graph shows the motion. Okay, because velocity we are talking about things similar like speed, right? Okay, so same thing is in one dimension along a straight line also. So for velocity time graph, the horizontal axis also shows the time and the vertical axis will show the velocity. Alright, V. Okay, so a horizontal line graph indicates that the velocity is so similar to our displacement time graph just now. But now, if let's say this is our V and this is our T, right? Okay, so if let's say it's a horizontal line, so what do you think? So which means that the velocity remains the same all the time, right? So that's why the velocity is unchanged. Okay, so if let's say the velocity is unchanged, meaning that the particle is actually moving at a constant speed. So meaning that the speed doesn't change or constant velocity is they are basically the same thing if let's say we are referring to the graph. Okay. Yeah, so it's either like negative or positive lah. That's the only difference, but the magnitude will be the same. Okay, so if let's say the line is not horizontal, similar like ST graph, it indicates that the velocity is actually changing. Okay, so if the velocity is changing, then meaning that the steepness of the line will tell you how quickly the velocity is changing as well. Okay, so the steeper the graph, meaning the larger the gradient, then which means that the uh, velocity is getting larger and larger in a faster rate. Yeah, so that's the idea. Okay, so similar, if let's say we know that the gradient of the ST graph meant for velocity, and we know that acceleration is actually velocity divided by the graph, divided by the time as well, right? So that's why if let's say this is our graph, okay, so we are only talking about the constant one, so which means we do not have more than one different gradient happens in the graph. So which means that the acceleration that you get, then you will be using the v divided by the t as well, right? Because like v minus t over over t minus v is going to give you the gradient. So that's why the acceleration is actually the gradient of the velocity time graph. Okay, I guess it's pretty straightforward. So S over T, so gradient for ST give you velocity. V over T, so gradient for VT give you acceleration. So by using the formula, we also know that velocity is equal to displacement over time. So if let's say we try to rearrange it, then we can get that displacement is actually equal to velocity multiplied by the time, right? So let's try to understand it by using this simple graph. So if let's say we are talking about constant velocity, okay, so you can imagine if let's say this is 5 and this is 4, So this is our velocity and this is the time, right? So how do you find the displacement then? So which means that this particle actually travel 4 seconds with the same velocity, which is 5. So if let's say you want to find the displacement, then you will just use 4 multiplied by 5, right? So what is 4 multiplied by 5? Is basically the area under this graph. So that's why displacement is the area under graph for a velocity time graph. So that's the difference between this graph and also the ST graph. So for ST graph, when we want to find the displacement, we try to understand where is the position for each turning point. Then we try to add them up together, or we try to see what is the net change. But for velocity time graph, if let's say we want to find the displacement, we calculate the area under the graph. Okay. Yeah, so a straight line on a vertical time graph indicates a fixed gradient. So if let's say the gradient is fixed, so which means that you have a constant. I'm sorry, I'll try to remove this in your handout. Yeah, I think it's the color thing when I try to do the blank. Okay, so therefore it indicates a constant acceleration. So which means no matter is like this or no matter is like this, so these are all the straight lines, so they have a fixed gradient, so it indicates a fixed acceleration in VT graph. So if let's say there's a curved line, so meaning that the acceleration change because you do not have a fixed gradient, right? So that's why the rate of change of the velocity will be changing according to the time, and that makes the change in acceleration as well. Okay, so now before we look into the interpretation of a graph like the ST graph just now, just a pretty quick notes here. Okay, so yeah, I just want you to have a very good idea for how to differentiate these two graphs and not to confuse yourself. So if let's say we are talking about a constant velocity, how is the graph looks like in a ST graph? A constant velocity, which means it will be a constant gradient in ST graph, right? So the graph will looks like this. It's a straight line. Okay, so yeah, it's either you start from zero or not lah, but the idea is it's going to be a linear line that goes like this. It cannot be a horizontal line, so you must make sure that. And for velocity time graph, what happens if let's say is constant? So which means the velocity doesn't change, right? So it will be a straight line, a horizontal line graph. So same thing for constant acceleration in VT graph. So which means it's going to give you things like this. Okay, because acceleration is the gradient for VT graph. So that's why having this sign, they will give you a constant gradient. Then for acceleration graph, it will be like a straight line because the acceleration doesn't change. So that's why it's a horizontal line. But in our syllabus, we are not going to look at acceleration time graph that much. So we are just going to focus in ST graph and also VT graph. Okay, so now same thing like previously, let's try to look at one simple diagram of velocity time graph. Okay, so same thing, we are going to interpret this VT graph together. So yeah, we have this graph and there are some simple information that we can try to extract. So for example, the acceleration, then by using the area, then we can get the total distance, total displacement, and by using this result, it can help us to get the average speed and the average velocity. Okay, so let's start with the acceleration. Yeah, so from the notes just now, we know that acceleration we can actually find it by using the gradient for a VT graph. Okay, so it's the same thing like the to find the velocity in the ST graph. So we are only looking at the constant acceleration only. So for the time period here, you will see that I'll actually put it in a stage where you do not have two different gradient that involve, because for that one you would need to do average. Okay, so let's start with from 0 to 1. Yeah, so you can see that obviously there's no change in velocity. So logically, you know that your acceleration should be 0. If let's say you want to calculate the gradient, then it will be 4 minus 4, right? Then after that, divide by the time, 1 minus 0, and we'll be able to get 0. So the acceleration is 0, which means that there's no change in the gradient. There's no change in the gradient as if there's no change in the velocity. Okay, then after that, from t equals to 1 to t equals to 0, so it's over here. So you can see the gradient is negative, so that's why you can predict that you will actually get a negative acceleration. So here is 4, then is 0. So 4 minus 0, then 1 minus 2 for the gradient. So 4 minus 0, and then 1 minus 2. Then we'll be able to get 4 divided by negative 1, and that will give us negative 4 meter per second square. Okay, and the last one, 5 to 6. So it's at the end here. Okay, so you can see this is a positive gradient, so that's why the acceleration will be positive. So it will be negative 2, all right, minus 0. So I'm using this to minus this, so that's why it will be 5 minus 6. Okay, so we'll get negative 2 divided by negative 1, and they will give us the answer for positive 2 meter per second square. Okay, so I guess this is quite straightforward. It's all right. Okay, so now let's try to look at the total distance. So yeah, the notes just now tell us that we can find the total displacement or the total distance by using the area. So now let's try to look at t equals to 0 to t equals to 2. So it's over this part. So you can imagine that if I'm going to find out what is the distance from t equals to 0 to t equals to 1, then I'm going to find the area for this rectangle. If t equals to 1 to t equals to 2, it will be this triangle. So you have two choices here. So either you can find rectangle plus triangle, or you can straight away combine them together, and this is actually a trapezium, right? So that's why the total distance here, we can use the formula of the trapezium, 1 over 2. Okay, then the distance of the two parallel line, it is here. Okay, so which means this is 1, and then plus 2, and then multiply by the height, which is 4. So that's why 1 plus 2, and then multiply 4, and we'll be able to get 6 meter. Okay, after that, how about the displacement? Yeah, so the working is the same. So displacement, the only difference is that you need to take into consideration for positive and negative. So is there any negative number that occurs here? No, right? There's no negative number involved. So that's why the total displacement will be the same, which is 6 meter. Okay, so now let's try to look at the second one from 2 to 6. So from 2 to 6 is over here. So you can see this is a trapezium as well. So we can show away. If let's say you want to do, you can also do like triangle plus the square here, then plus the rectangle here, then plus another triangle. But the easier way, of course, is to use trapezium lah. So the length here is 6 minus 2, so it's 4, and then here is 1, then the height is 2. So that's why 1 over 2, and then 4 plus 1, and multiply by 2. And we will be able to get 5 meter over here. Okay, so how about the total displacement? Yeah, so this is some a bit different from the first one already, because the number here, the height here, for the distance, we are getting the positive number. I'm sorry, this should be negative. Yeah, perhaps some mistake for my drawing there. Okay, so yeah, it's negative 1, negative 2. So that's why when you try to calculate this, you should take into consideration for the negative as well. So this should be negative 2. So your answer will be negative 5 meter. So which means that from the time 0 to 2 seconds, the particle actually moved to the positive direction for 6 meter. Then after that, it moved towards the negative direction for another 5 meter. So that's the idea. And normally, how can you find it is that as long as the area occurs on in the positive axis, right, then it will give you a positive displacement. If it's at the negative side, then it's going to give you a negative displacement. So this is how you check that. Okay, so now we are looking at the total, so meaning from 0 to 6. So we have 0 to 2 and 2 to 6, right? So which means the total distance we can plus together, okay? So 6 plus 5, and that will give us 11 meter. So for displacement, yeah, we must make sure we are looking at what is the net change. So at the starting point, it moved to right for 6. Then after that, it come back for 5. So what is the difference now? So it's like here, then you move 6, then you come back another 5. So which means the difference here is going to be 1 only. And is it positive or negative? Yeah, it's going to be positive, right? Because this is here. So this is positive side as well. So that's why 6 minus 5, and we'll be able to get 1 meter. Okay, so for average speed, we'll be able to use the total distance to just help us to do. So you can see that the timeline here is all the same, so we can straight away get to the answer. So for the first one, the total distance is 6, right? So that's why 6 divided by 2 seconds, so it's 3. Okay, so average speed, so meter per second. Okay, then the same thing here is 5, so that's why 5 over the time interval here is 4 seconds, so that's why 1.25 meter per second. And the last one, the total distance here is 11, right? So 11 divided by 6. Yeah, you can try to get the decimal by yourself. Okay, so for average velocity, then we'll be using the total displacement. So 6 divided by 2. So this is how we get 3 also. So you can see that there's no difference here because they are all in positive direction. Then after that, for this one, then it's negative 5 over 4. So your answer will be negative 1.25. So the last one, because the net change in the displacement is 1 only, so that's why 1 over 6. You also can try to get your answer by yourself. Okay, so that's the part for this. So now we are going to look at four example together. So the first two will be relatively easier, I think. Then after that, the last two will be the harder questions. So if let's say you are confident enough, then you can always try out all the example first. Then after that, you can check your answer by continue watching this video. Okay, so let's try to look at example 1. Okay, example 1. A car moves forward on a straight road from a point O at a constant velocity for 20 seconds, traveling a distance of 60 meters. Then for the next 20 seconds, the car is stationary, remaining the same position, right? Then after that, the car returns to O, which takes another 10 seconds. Okay, so A, the question wants us to sketch a ST graph for the first 50 minutes for the car's journey. So you can try to take out some important information, then roughly you know that what is the ratio or what is the numbers that you should have on your graph itself. So you can see that the time is like 20 seconds, after that next 20 seconds, then another 10 seconds. So you can always try to draw your graph like 10 seconds per interval. Okay, so this is for A. So we can try to sketch the graph first. Yeah, and you can try to imagine, do you think that it involves any negative displacement? So you can imagine that this thing is moving forward, so it's in a positive displacement, then it keeps stationary, then go back to O. So you can imagine that basically for this graph you wouldn't have any negative displacement. So for the interval, then we can try to put 10. So 10, 20, 30, 40, and also 50. Okay, so let's try to look at the first one. So it moved forward at a constant velocity. So you should remember, for constant velocity in a ST graph, how is that going to look like? Yeah, it's going to be a straight line, right? So that's why for the first 20 seconds, traveling a distance of 60. So that's why here is 60. This is for our S, and this is for our T. Okay, so which means for the 20 second, it can reach 60, right? So with a constant velocity, so which means the graph will look like this. Then after that, it keeps stationary for the next 20 seconds. So until 40, it's going to be stationary. So the displacement doesn't move, doesn't change. Then after that, it returns back to O. So which means from 60, it go back to 0, which take another 10 seconds. So from 40 to 50. So that's why like this. Okay, I think it's pretty simple. So after that, B, use the displacement time graph to find the velocity of the car during each stage. Okay, so what is that meant by each stage? Yeah, so as what I mentioned before, if let's say you want to use the gradient, it should be the constant velocity only. So the different stage will be stage 1, stage 2, and stage 3. Okay, so from the time from t equals to 0 to t equals to 20, then what is the velocity? Then we can try to use the gradient, right? So this one is 60 minus 0 divided by 20 minus 0, and we can get the answer of 3 here. Okay, then after that, the next stage will be 3 equal to 20 to t equal to 40. So you can see that the displacement doesn't change, and that means that there's no change in displacement with respect to your time. So which means your velocity will be 0. Or if let's say you use 60 minus 60 divided by 40 minus 20, you are going to get 0 as well. Then after that, for the last one, the last stage is going to be t equals to 40 to t equals to 50. Okay, so this one, same thing. We need to calculate the gradient, and don't forget that you need to have your negative, right? So V will be equal to, so here is 60 minus 0. So that's why it's going to be 40 minus 50. Okay, and that will give us the answer of negative 6 meter per second. Alright, so that's the part for number one. I think it's pretty straightforward, but as you try to go through your past year paper, you will actually realize that for this kind of graph, right, normally I mean, compared to the percentages that the question come out, actually VT is more than ST. So meaning velocity time graph is actually comes out much more often than the ST graph. Yeah, but you will need to know both lah. But eventually, ST graph is going to be easier than VT graph also. Okay, so let's try to look at example 2. Alright, number two, this is a pretty straightforward example as well. Okay, so the car accelerates smoothly from rest for 30 seconds to a velocity of 20 meter per second. So continues at a steady velocity for 20 seconds, then it decelerates to rest for in 20 seconds. So the question wants us to find the velocity time graph. Okay, so that's why for this question, it will be easier that for us to just draw an interval of 10 as well. Okay, so A, so this is for VT graph. So same thing, you can imagine that it accelerates until this velocity and it keeps at the steady rate. Then it decelerates. So that's why you shouldn't have any negative velocity involved also. So the graph will simply look like this. Okay. So 10, 20, 30, 40, 50, 60, and 70. Okay, so until the velocity of 20, and I guess that's enough. So this is V, and after that, this is T. Alright, so now same thing here. So which means that from the starting, right, the car is actually from rest. So from rest meaning that it will start from the velocity of 0. Then after that, it accelerates smoothly. So that's why, which means that the acceleration is a constant one. Then after that, it accelerates like with a constant speed. So you know that the graph will be a straight line as well, then to the velocity of 20. So for 30 second, right? Yeah, for 30 second to a velocity of 20. So 30 second, 20. So it's like here. So accelerate. Okay. Then after that, it continues at a steady velocity for 20 seconds. So which means from 20 to 50, it keeps at the same velocity, which is 20. Then it decelerate until rest. So rest, which means V equals to 0 lah, for 20 seconds. So that's why from 50 to 70, decelerate. Okay, so that's the part for A. Okay, B, calculate the acceleration in the first 20 second and the final, first 30 second and the final 20 second. Okay, so this is the first 30 and this is the final 30. I think this is very straightforward also. It's just to find the gradient. Okay, so for the first 30, for first 30 second, so the gradient, so which means A will be equal to, so let's just find the gradient. So 20 minus 0, then divide by 30 minus 0. So we can get 2 over 3, which is 0 0.667 meter per second. Okay, then after that, for the final 20 second, so you can see that the line is having a negative gradient, right? So that's why you should have a negative acceleration. So A will be equal to, so same thing, 20 minus 0, and after that 50 minus 70. So that will give us an answer for 20 over negative 20, so which is negative 1 meter per second square. Okay, then we continue to C. So calculate the total displacement. So total displacement in VT graph is basically the area under the graph. So it's basically here. So you can see this is a trapezium. So yeah, you can always use triangle plus rectangle also, but that's unnecessary lah. So yeah, total displacement will be just equal to the area for trapezium, which is equal to 1 over 2, and the length is going to be 70, and then the top part is from 30 to 50, right? So that's why 20. So multiply by the height is 20. Okay, so we can solve it and you will be able to get the answer of 900 meter. Okay, so D, if you are finding the average speed, meaning you need to use the total distance, and then after that to, oh, so make sure that because this is total displacement, right? So there's no any negative involved, so you don't need to minus off, it's basically everything up there. So total displacement and total distance is just the same in this question. So for average speed is the total distance divided by the total time, right? So since the total displacement didn't involve any negative part, so the idea is just the same. So 900 divided by the total time involved is 70 seconds. So 12.9 meter per second. Okay, so yeah, that's the part of this question. So always make sure that for average split, you must, meaning that you have no choice but to use the area under the graph to help you to find the displacement or the distance first, then you only continue. Because by having this one, right, we cannot, don't ever do that like 20 plus 20 and plus 0, then you see that there's like 3 point, then you divide by 3. Yeah, so we cannot do that. So make sure that you are getting the total or then divide by the total time. Okay, so let's move on to the last two questions. All right, number three, a ball is projected up a smooth plane at a velocity of 15 meter per second from a point origin. So the ball decelerates at a constant rate for 6 seconds, and the ball is instantaneously at rest at t equals to 3. Okay, so this question is a bit special in the terms where you need some of the uh, basic knowledge in physics perhaps to help you, or we'll kind of look at this situation in a much more later lesson, but to give you a good idea, I think this question is very interesting for us to go through. Okay, so I think if let's say you didn't know anything, right, you can always sketch the velocity time graph as well. So you know that the ball decelerates at a constant rate of 6. So which means what happened here is that you will have the negative part. Okay, so let us try to draw the motion, like how is that going to look like. So you have a ball. So which means what happened is the ball is like being projected. So it goes up until it reach a point. So this is like the maximum point here. Okay, then after that, what happened when it go down? It will, the last point that it has is like go back to the point where the origin stage, right? So there's some knowledge that you might need to know is that normally when the particle at rest, so meaning when the velocity becomes 0, that will eventually be the point where the particle change direction. So you can imagine things like this. So for example, if let's say you try to drive a car, so when you try to do a U-turn, right, you must try to slow down. Then after that, that's the time that you that's a very short time that the velocity will eventually become 0. Then that's the part where you change your direction. So it's the same thing for the normal particle situation as well. So which means you can imagine that when this thing going up, right, when it reach the maximum, then the ball will goes down. So this is the part where t equals to 3, which means the ball stops for a while, then after that it goes down. Okay, I mean obviously we can't observe the short while there because it's relatively very short the time, but the idea is that the ball will reach the velocity equals to 0 when it change direction. So you can see that the ball decelerates, so that's why in the form of dt graph, right? Okay, what happened is that you will have a negative acceleration, meaning negative gradient. So it start from 15, then after that it decelerates, so which means it will just keep on going like this. So the idea is here is the part where you reach the v equals to 0 because instantaneously at rest, which means v equals to 0. So that's why v equals to 0 happened here, and this is our time equals to 3. So you need to continue to decelerate, right, until the so it at a constant rate. So that's why you don't need to change the straight line. It's just basically the same straight line with the same gradient, which give you the same constant rate for your acceleration. So here will be your 6. So that's why since it's a constant rate, right, then you can imagine that at here, you will actually reach negative 15. Okay, and it makes sense also if let's say this is negative 15, which means the area under here and the area under here is just the same. So that's why the displacement going up and the displacement going up. So positive and then negative. Okay, so I hope that you can get the rough idea. Okay, so B, calculate the value of the ball's acceleration. Okay, so acceleration. So that's why I think this question is just to find out the gradient, right? So the acceleration here, A will be equal to 15 minus negative 15, and then 0 minus 6. Alright, so yeah, you will have a negative answer because this obviously is a negative gradient. So 30 divided by negative 6. So we'll have our answer negative 5 meter per second square. Okay, so see what is the maximum displacement for the ball. Okay, so this is our origin, right? Alright, this is from the point O. So when you project the ball and it reach here, then this obviously is the maximum velocity. Sorry, it's going to be the maximum displacement because after that the ball comes down, it changed direction after the v equals to 0. So that's why at this point, then this is the point that the ball reached the maximum displacement. So how do you think that you can get the maximum displacement? Then you will need to refer back to this graph. So VT graph, if let's say you want to get the displacement, then you need to find the area. So that's why you will need to find the area under the graph from t equals to 0 until t equals to 3, which is basically here. Okay, so I hope that you can understand why didn't we plus them together, because you are just finding the maximum velocity, the maximum displacement, right? So meaning from O until here, then what is the maximum height here? So that's why by using the area, so we can get that the maximum displacement will be just equal to the area for the triangle here, which will be equal to 1 over 2 and then 15 multiplied by 30. Okay, sorry, multiplied by 3. So this is how you can get 22.5 meter. Okay, so that is the maximum displacement. So D, what is the total distance? So which means it go down, then fall down. So since it's a constant rate, so that's why you can imagine that the area here will be the same as well. So the total distance for the ball will just be equal to 2 multiplied 22.5. So you can get the answer of 45 meter. Okay, so I hope that my explanation is clear enough. If you have any further question for this one, then you can let me know. Okay, so let's try to look at the last question. Okay, question 4. Yeah, so this is also a past year question from paper 4.2 for May and June 2020. Okay, so yeah, I just take out one question so that you can like reduce one question, and I hope that to go through with you this question as well to see like the pattern of the question is actually the same thing. It isn't that difficult as well. Okay, so a tram starts from rest and move with uniform acceleration for 20 seconds, and it travels at a constant speed for 170 seconds before being brought to the rest. So meaning brought to rest, meaning v equals to 0 lah. So with a uniform deceleration magnitude that twice the magnitude of the deceleration is twice of the acceleration, and the total distance traveled by the tram is 2.775. Okay, so sketch the velocity time graph and stating the total time for which the tram is moving. Okay, so A, so same thing. Let's try to find out the important point here. So you can see 20 seconds. Then for another 170. So you can imagine if the last one is going to be deceleration at the magnitude twice. Okay, maybe let's try to do the first two one. Then after that, I try to explain from there. So we have this line, so and the other line. Okay, so obviously we are going to have 20, right? Then after that, another 170. So that's why we have 190. Okay, so you can imagine what happened here is uniform acceleration. So which means start from rest, uniform acceleration meaning straight line for 20 seconds. Then after that, it travels at a constant speed v, right? So that's why for the first one, you will accelerate until it reaches v. Okay, then after that, for 170 seconds, after that, it's going to be a constant velocity. After that, what happened? It decelerate, but the magnitude is twice. So what happened? You can imagine that if let's say you need 20 seconds to reach this velocity, then how much of the time that you need to decelerate so that this graph goes back to v equals to 0, and it's going to be a uniform as well. So that's why if this take 20 seconds, right? So which means if the magnitude is twice, meaning that it will use half of the time. So this is going to be 200. Okay, and then this line is going to be like this. So you must show that this line is going to be much more steeper than this one, because this is at 20 seconds, right? Then this is 10. Okay, so the idea of this graph is if it's given like 2 marks, then one will be your graph, then the other one is to show that this line is actually having a gradient larger, or is a line that is steeper than the first line. Okay, so this is how you get your A. Then stating the total time, so this is the total time now, which is the 20s. Okay, so now we'll be looking at the B. So find the V, so meaning the velocity. So one information that given by this question is the km here. So which means we can use the idea for total distance equal to the area under the graph, then you can get the V. Okay, so for VB, the total distance is 2.775 km. So we are just going to change it to meter, so 2775. So this is a trapezium as well. So 1 over 2, and the parallel line is 20 to 190, so 170, and then, 170 and then plus 200, and then multiply the height, which is the V that we want to find. So 2775. So by solving this, then you will be able to get the answer of 15 meter per second. Okay, then C, you need to get the magnitude for the acceleration. So I guess this is easy after you get the answer for B. So basically you are just finding the gradient here. So acceleration will be equal to 15 divided by the time, which is 20. So you can get 0.75 meter per second square. Okay, so that's the acceleration. So the idea for magnitude of acceleration is just that if let's say you are finding this part, right? So this is magnitude of deceleration, so which means you do not need to have any negative lah, because we are just finding the magnitude. Yeah, so that's the idea. Okay, so you have like 6 questions for the past year question. Just spend some time to finish it. So if you have any question, let me know. So yeah, I'll see you in next week class. All right, take care and thank you.